This is the lab class which is being recorded uh, for the Power System Lab 1. And for the today class, we will have the simulation talks on load flow studies. And for this case, we have a manual prepared which gives you instruction what is to be done in the class and what we are expecting from you at the end of the class. You have to visit the website which is referred here. I will just share the website I have already opened for you. And you have this website. And from this website, you just go to the free download. And when we click on this, there is a zip Excel file which will get downloaded on your system. And then when you click on this, we have some instructions how this Excel sheet can be used for load flow study problem. So you have to download, you have to unzip, and then again, depending upon what is the Microsoft Office installed in your system, computing system, you may be required to have some setting on the tool. So you referred this, it is very clearly given here that go to the Excel sheet, Excel file, and then you select the tool from the top and then add in and tick analysis for tool pack analysis and so on. However, for my case, which I have here, when I have this Excel file opened for you, uh, I have this is the first sheet, which is the introduction, which gives you introduction about the Excel sheet here. So this will be the Excel sheet which will be available to you for your study. Now going back to the manual, so you get the Excel sheet downloaded from this website here, and then in the manual I have given what are the instructions that you should follow to download and then open the Excel sheet here. And then again, it gives you information how we can use the Excel sheet for simulation. So this is by pressing F9 key. But as I said that depending upon the Microsoft Office, you have to refer to the tools here. But in my case, the Office which I have is I can show you. I do not require to have this. I can directly go to my calculation option here, right? It is in manual mode here. And then we go to the theory part. So I think last semester we discussed the topic on load flow analysis. And I have discussed how we can perform the load flow analysis, because in the load flow analysis we are interested to have the some quantities, some unknown quantities determined. So you have a network, and so if you remember, we have this single line diagram of a network. So you have a generator on the bus 1, another generator on bus 2, and then you have a load on the bus 3. This network is represented as a equivalent circuit as shown in here. And then if you remember, last semester we discussed about how we can, because this line will be represented by the impedance of the line here. So that means the impedance parameter referring the resistance of the line and inductance of the line. So following the equation that we call it as nodal voltage quantity at a given bus, and then we can know what are the current flow in each lines here. But if we have the equation in terms of the current variables, then we have to convert the impedance of the line into admittance of the line. So this is what we write for the current following the KCL law. So you have the current or the power injection at this bus. So we write, because this bus is connected to 1 and 2 and then 1 and 3 buses. So you have the Y12 and Y13, and then other part. It is negative of the admittance for the V2, and then same way for V3 here. So these will be the off diagonal elements, if you remember, in the admittance matrix, and this will be in the diagonal elements in the admittance matrix. And thus we can write the complete set of the equations for the branch current if you have n number of branches in the network. So as I said that now you have the current vectors, admittance matrix, and then the voltage vectors here. So that's in the matrix form we can write here. So this Y is your nodal admittance matrix, and this is your diagonal admittance matrix, and this is your off diagonal admittance matrix here. So if you can recall, and then if you remember in the bus network when we have, so if for some cases we have the bus network as load bus, and some cases we have the buses referred as a generator bus, right? So thus depending upon whether you have a load bus or the generator bus, or again, if you remember, we also had a slack bus. So if there is a 3-bus network, and there has to be one of the bus as a slack bus, and normally it is the generator bus we consider as a slack bus here. So we will have that way, and then we will apply, let us say, the Newton-Raphson method for the load flow analysis, and then with the branch current obtained for a particular branch. So it will be the product of the admittance of that particular branch to the voltage associated with the bus. This is how we write the complex power, and then we have it written in terms of the angles here and the voltage magnitude, because we have transformed this admittance matrix in terms of the voltage quantity and the angle here. And then we write the active power and reactive power here. This is the real part and the imaginary part. And then whatever the quantity which we have, we take the difference. Yeah, so that means what is the injected power at a particular bus, and then what you have calculated. So the difference of the two power, that gives you the error in the power, or this can say the estimation error of power and the reactive power or the active power. So we are actually interested to estimate some of the unknown quantities here, because if you remember, I think in the network system, here some quantities may be known, some quantities may not be known. Let's say, for example, voltage magnitude, rotor angle delta, then we have active power, then we have reactive power. So depending upon where you have if you have the bus as a slack bus, if you have a bus as a generator bus, or if you have a bus as a load bus. So these four, out of these 4 quantities, 2 quantities may be known and 2 quantities you have to determine in some cases. So in the case of Newton-Raphson method, we do the steady state analysis, and then for the power error and reactive power error, we have the partial differentiation of the power with respect to the angles here. and then same way on this side it is the with respect to voltage. Same way we applied it for reactive power. And then I will not discuss today gaseous cylinder meter. We will have it for the next turn. Then here this step here, this section gives you a step procedure how you will use the Excel sheet for the load flow analysis. Now remember one thing, if you have the sheet 1, then this is your sheet 1. So in the sheet 1, there, as it is said, you have some with color code format. So you have green are the places where you can enter data, number you are able to change, and then that is shown in the red color here. We will this go to the later on this part. Then another sections with the yellow backgrounds which shows the result of the calculations. And then, as I said, this sheet 1 is for introduction. So we have some theoretical background given on the sheet 1 here, which I have included in the manual. We move to the next sheet here. So in the sheet 2, you have the problem statement, what we are supposed to do. So if we refer, uh, as I said, that there is a color code format. So if you refer here in the sheet 1, it is said that what is the blue part, what is the green part, and the red part, and then the yellow part here, yellow shade background here. So if you go to the blue part, it is only, it says that gives you information about the section. Then this green is the section where you can enter data, and the value which is can be modified, it is in red color here. So we have some information here, and as shown that this is a 3-bus network. So we have a slack bus. For the case of slack bus, we have the voltage defined and phase. So let's say this is your slack bus, bus number 1. So you have the voltage, magnitude, and the angle defined. So these two quantities are known. For the generator bus, which is bus 2, we have the voltage magnitude, input power defined. So voltage, this is the voltage magnitude, and input power, it is defined. So delta 2, it is unknown here at generator bus. Then we have the load bus, bus 3, for which P active power and reactive power, they are known. And thus we need to determine what is voltage V3 and delta 3. So for this system, as you can see, we need to determine rotor angle delta 2, and then it could be for the initial condition, in fact, and then we want to know what is V3 and delta 3 here. So all these quantities, they are in per unit. And then if you refer, it is said here that green background part. So this is the green background part here, this section, where you can edit the value. So the value which can be edited, it is in red font here. So you have the line impedance for the network. So you can change the line impedance of this line. You can have it any value here. Let's say you can add, I delete it, and then uh, I delete it, and then let us write I have it 02 here, right? So that way we can do. So I have changed it here, right? And then but then this is to be modified here. Okay, this is so thus if you modify the impedance, then you have to the change value of impedance as well. Okay. Mm. I think it's stuck. Mm. I change it this way. What is this? It's complex three round imaginary. Okay. So this, in fact, if you change the value of impedance, so this admittance of the branch will be calculated automatically here. So you don't need to do anything here, right? And then, as I said, then you can have the applied Newton-Raphson method in the sheet 3 here. So if you go to this, so you can also do the numerical calculation manually. So with the change value, and as I said that it is possible to have an initial value. So you can change these values here. If I change this, let's say, I can make it how much? 4. If I have it here, just a minute. This one. So I make it 4 degree, and here I make it 0.9 here, right? And then I make it this one, let's say 10 here. Okay, so this the initial conditions are defined here. So now the yellow part which is set, that will give you the calculation here. So thus you have in fact you have modified the impedance here, and that's the admittance. You got it. Okay, what is this problem? I think should be, and you have this kind. So this is the operating condition which you get from C2 here, right? And now if you do the manual calculations following these equations, then in the first iteration you get this result, and then in the second iteration you find the Jacobian matrix here, and then you get this much error, and then you move to the next iteration. So thus the error can reduce further, right? And then following the third iteration, fourth iteration calculation, and fifth iteration calculation. So finally, after fifth iterations, you will get this result. So here is the summary of the results for delta angle V3 and delta 3. So if you remember here, as I said that we want to calculate delta 2, V3 and delta 3. So these three are the unknown quantities. So we have finally determined all these quantities over here. And then we have also written what are the voltage quantities of the 3 buses. Now we want to simulate here. So you can refer the formula, but again, I'm not sure, depending upon the version which you have, right? But in the manual, if you refer, so this is what I have discussed actually, right? And then here in the instruction sheet, you have to press F9 to run the simulation here, right? So if you press F9, yeah, so actually, oh, okay. So there was a mistake here. That means here, because I have this quantity not known actually. So it has to get from here. So I think I need to have this calculated. So if I say 0.02, you have it 0.02, it is something if I make it, this is 0.01, 0.02, 0.25, this one, and then, so if I just make it 0.01, okay, I think I had a mistake here only. Should do it automatically, but I have changed it actually. What is YY12? Okay. Okay, let me close it and then start again. That is better way. Okay, let me do it again. Here, okay, I have it here now as 0.1. I will show it for this 0.02. I have changed it, and then you can see that admittance, you have to modify it here, right? You get it. So with the change value of impedance, you can modify the admittance, right? And then again, you can also change these operating conditions here. So we move to this with these parameters, we move to formula, and then with the calculation, we have set it as manual with this, and then we click on this, and then we press F9. So you can see that when we have pressed F9 key from the keyboard, then with the change parameters, what we have referred here, we are able to get the change value of these unknown quantities. So if I make another, let's say something here, so let's say I add it 1.05. I have changed the ID. Okay, it does not take it. So I let, if I make it 0.95, let us make it. No, enter operating condition says, I think where it has to be. Okay, this is fixed, but I think I have it for you, saying that you modify P to S. So I modify this and I make it to 1.2. Let me see. Okay, now it's done. And then you click on this sheet 3. We keep these angles, everything as it is, and we see what are the change values of unknown quantities after 5 iterations, and I press the key F9. Okay, but there's no change here. But if I make it again, right, and I press F9. Okay, so you can vary 0.95, 0.96, but I'm not sure if you can do that, make it 0.9. Okay, and then I didn't save it last time actually. Better, but you can do. And then I press F9. Okay, it is done. And then see the answer. Or you can also, if I make this, let's say -10 initial degree. So with that, when you do the simulation, I press F9. So here you have the changes in the calculation of the quantities. So that way you can do some more analysis and then see what are the changes you have. Now this has to be delta 2 here. I have no, this is delta 2 angle. So first part is that you calculate delta 2 V3. So I have given you what could be the parameters and then initial point, because here it is the system parameter. This is this operating point, operating condition initially. So for this, what are the values of the unknown quantities? And then you can also vary the operating point and then see, however, the system parameter keep it constant, and then you can analyze how does the delta 2, this one will vary with the changes in the power here. So you can analyze that part. You can make it to 0.9 it is, or if I make it 1.2. Okay, 1.2. I made it. And then I mix. Yeah, so just changing the power, we can see the quantities have also changed. So that way you can simulate here. Right, so I end with the recording, and then you have some more tasks given in the manual sheet, and which you can refer and then complete the tasks. So